All right, let's do it using mean value theorem. Let's use an example where f of x equals the cube root of x. We're going to look at it over the interval 0 to 8. We're going to verify mean value theorem, and we're going to find c. So f of the cube root of x is continuous everywhere, which includes 0 to 8. It's also differentiable everywhere, which includes 0 to 8. So we meet the criteria of it. So that means there exists at least one c in 0 to 8 such that f prime of c equals the slope between the 2 points. 0 f of 0 and 8 f of 8. So take a look at this. The derivative of f of x is 1/3 x to the negative 2/3. If we rewrite it as a radical, we've got 1/3 times the cube root of x squared on bottom. We do need f of 0 and f of 8, so I found them here. F of 0 you plug in, cube root of 0 is 0. We plug in 8, the cube root of 8 is 2. So we've got the point 0, 0 and 8, 2. F prime of c has to equal some m. So we're going to find out what that is. Plugging in our points that we had right here, we've got 2 minus 0 over 8 minus 0. That equals 1/4. If we're trying to find the c, we plug in c for our x's. So I've got 1/4 equals 1/3 times the cube root of c squared. So what I ended up doing is I cross multiplied. And I just cross multiplied the cube root part. I left the 3 over there. Okay? This might be better with a regular pen here. So that cross multiplied there, that cross multiplied there. And I get cube root of c squared equals 4/3. So if I cube both sides, I get rid of the cube root. So c squared equals 4/3 cubed, which is 64/27. If I take the square root of that, square root of 64 is 8. And square root of 27 is 3√3. So I've got c equals 8/3√3. If you rationalize this, you multiply by √3/√3. Just as a reminder, we get 8√3/9. If you throw that in a calculator, you get c is about 1.54, and which is definitely inside 0 to 8. Okay? Want to get rid of my circle marks there. If we take a look at the picture, the red line, that is our cube root function. And this line here is the secant line from 0, 0 to 8, 2. And I literally found, when I made the line, I moved the blue line out of the way and I made a green line from 0, 0 to 8, 2, and I dragged it and moved it up there. And that's right at about 1.54. We can see its tangent there. So they have the same slope. I didn't make the equation for the tangent line. I just know it's there. All right. Another example of this is velocity. Let's take a look at if we were to drive from COS Visalia to Disneyland. So I just did this today. I put this in, so whatever the traffic is giving me this. It says 4 hours and 25 minutes to go 209 miles to Disneyland in Anaheim, California. I made it 4 hours and 30 minutes so that maybe we have a 5-minute pit stop, and that way I can say 4.5 hours, which is what I put over here. So average velocity is like the average distance over the average time. And we calculate that by doing the subtraction in the distances. I've got a starting point of 0, 0. Like if I say xy is time and distance, when I start, I've gone 0 minutes and 0 miles. And by the time I'm done, I've gotten 4.5 hours and 209 miles. So we can make a nice little fraction out of that with M, our ending point minus our beginning point over our ending time minus our beginning time. 209 over 4.5 is 46 and 4/9 miles per hour, or 46.4 with a repetition bar above it. So that's an example of like applying it, which means the average velocity over the entire trip was 46.4 miles per hour. That's what like my car is going to tell me when I'm driving. That means at least there had to be at least at some point of time on the drive where I was going exactly 46.4 miles per hour. I may have sped up to 70 miles an hour, but there's times where I was going slower, like when I took the surface roads and exits and stuff like that. So there's at least some point. That's doing it without equations. Let's look at the problem with equations. Suppose a ball is dropped from a height of 200 feet. Its position at time t is s of t equals negative 16t squared plus 200. Find the time t when the instantaneous velocity of the ball equals its average velocity. So we need to find the average velocity, and that way we have something to set the instantaneous velocity equal to. Average velocity will be s at 0 seconds minus s of t0. That's like a position 1 minus position 2 over my time. I'm t0. That looks funny. I want to change the way that looks. Where t0 is when the ball hits the ground. So like s of t equals 0. You'll notice if I stick in 0 here, that's a 0. I get 200 for s of 0. So s of 0 is 200, and I need s of t of 0. I solve for that right here. So I plug in t0 for my equation that we had up here. And when I do that, I add 16 t naught squared to both sides. I get 16 t naught squared equals 800. Solve for t naught squared, which is 200 divided by 16. I reduce that to 50 over 4, which is 25 over 2, which is 12.5. You could have done that in a calculator, but I try to not do math in my head. I try to do the math in my head when I can. So T naught is exactly square root of 12.5, and that's approximately 3.536 seconds. So that's what I needed on bottom right here for my T naught. My square root of 12.5. If I do that, I have 200. Oh, that needs a negative sign in there. Negative, because the bottom's negative. So where does that happen? I remember to put the negative here. We want to find where the instantaneous velocity equals the same thing. Instantaneous velocity is when we take the derivative. So what is the derivative of s of t? That is, oh shit, I wrote b prime. That's not right. B of t equals s prime of t. And taking the derivative, you get negative 32t. What we had up here is that negative 200 over square root of 12.5. I solve for t dividing by negative 32. We get, this is an exact value, but that's completely useless. So I calculated it's approximately 1.768 seconds. That's definitely between 0 and 3.53. So we found the time when the instantaneous velocity equals the falling velocity, or the average velocity as falling. We got one more short video. It's on corollaries, which are called, they're effectively like sub-theorems, or theorems that depend on previous theorems.